Hi, we're Group 11 and this is our EGB320 Group video for our soccer robot. I'm Harry Stone, I was in charge of the AI navigation. This is Courtney, she was in charge of vision, and Ryan on the end was in charge of drive system. Declan behind the camera was in charge of kicker and dribbler.
So the objective of this was to build a robot that could play soccer. So this involved locating the ball, avoiding obstacles, and then kicking a goal.
The specifications for the robot was that it had to fit within a 180mm radius and had to be no higher than 225mm. The robot also needed to obey the 80-20 rule for holding the ball and needed to not dynamically hold the ball. The robot had to be built with a project budget of $200 and a robot budget of $160.
So you can move, you can see stuff, but what if you actually want to do something? Well, that's the purpose of this section, AI and Nav. We want to find this, put it into this without hitting these and do it as quickly as possible. There were a few ways this could have been done, but in the end we decided to use reactive potential fields. A potential field is an array of dimensions one greater than the space you're trying to represent. We used a single dimension, theta. This was the angle bearing from the robot to the obstacle in question. Unfortunately, we didn't have 360-degree vision. We only had approximately 60 degrees. Coupling this with the forward placement of the camera meant that we had great difficulty in avoiding obstacles at times. One of the strategies we used was to move in a curve. This worked great in VREP, but was very limited when we tried to apply it to the actual robot. In the end, we used an obstacle memory system where the robot would remember if an obstacle moved outside the field of view and treat it as if it was still within that field of view. This allowed us to skirt around obstacles when we lost them and we were close. So anyway, in case you're wondering, I recorded this in the middle of the woods in the middle of the night because there is nowhere else in my schedule where I can fit this in.
The vision system is required to detect the ball, blue and yellow goal and obstacles in real time. Along with this, each object's range and bearing was required to be calculated. The approach taken for this was through HSV color spacing, by setting high and low color thresholds and finding their corresponding largest contours. From this, the XY locations, radius, distance, and angle were calculated. The final product was successful in fulfilling these required tasks. However, there were some inaccuracies and false positives that were present. To fix this in future projects, different filters should be tested along with setting more limiting parameters to identify each object. The main variable that caused these errors were the change in lighting throughout the day. The issue could be solved if the demonstration was run in a controlled environment with consistent lighting.
The kicker and the dribbler are the components that most directly deal with the ball, either handling it to let the robot move around or shooting it away to score a goal. They're also some of the most over-engineered generally. In a competitive setting, we'd be using one of these custom-made solenoids charged to 400 volts, but for cost and safety, a store-bought solenoid was used instead. This worked reasonably well when driven from a power supply, but there were issues with running it from the Raspberry Pi, so it was abandoned in favor of a spring-based kicker. This worked better and could be run with a standard motor controller, but was removed from the robot in favor of simply ramming the ball. This ram was less accurate and forceful, but the significant cost reduction made it worthwhile. The dribbler was used to put backspin on the ball and keep it with the robot, and also went through several iterations. There were problems with the initial design, dragging the ball under the robot instead of rotating it on the spot, so it was lowered to be below the ball instead. While this reduced the problem and occasionally worked effectively, it struggled to generate the backspin necessary, and a small pair of fixed arms were used instead. While it's clearly less efficient than a true dribbler, it was enough to allow the robot to meet the specification and score goals.
The robot was differential driven, which allowed for easy prototyping and lowered the budget. The PLA 3D printed motor holders, casters and wheels were environmentally friendly and saved money. The spiked wheels allowed for enhanced grip on the field. Our motor driver was the MDD3A from Cytron and was chosen for its cheapness and qualities, especially for its inbuilt braking, motor current rating and debugging features. 150 to 1 6-volt high-power Pluto motors allowed robot speeds from 0.03 to 0.6 meters per second, which exceeded their respective specified speeds. Hence, the robot had exceptional maneuverability at low speeds. The forward velocity and bearing from navigation and AI was converted into the robot's forward and rotational velocity, with PWM signals then sent from the Raspberry Pi to the motor driver. The painted and laser-cut HDF chassis was used for its robustness and sustainability. The robot had two sections secured with metal and nylon fixtures. The lower section housed the motors, wheels, laser gate, passive dribbler, and battery. The upper section housed the Raspberry Pi, custom 5-volt switching regulator, motor driver, and custom camera mount. The robot's casing wall incorporated a living hinge and an edge team number on the top.
In the end, we met most of the specifications. We were under budget at about $140, and we performed moderately well on the day. This was a great result for us.